Hello everyone, I'm Ziling, and thank you for your watching. Today I will presenting my research project on building a more efficient transformer architecture. As we know, standard transformer models relies on self-attention to compute the relationships between tokens in a sequence. However, this requires computing interactions between every pair of tokens. Uh, which will result in quadratic computation and memory complexity. When sequences become long, this scaling becomes very expensive. So my research project focused on addressing this limitation by exploring sparse attention mechanisms that significantly reduce computation while still preserving the model's ability to capture important relationships in a sequence. The proposed architecture to address this scalability issue, we design a high-performance sparse attention mechanism. The model uses binary tree structure to progressively compress input information layer by layer. This approach reduces the quadratic computation and the memory complexity of standard attention to approximately big O n log n. The attention mechanism consists of two components, hierarchical sparse attention and the sliding window attention. Instead of computing dense global attention across the entire sequence, the model divides the computation into two stages. A bottom-up tree construction, parents to children, we call it phrase, and the top-down children to parent phrase, context propagation phrase. This design allows a model to approximate the global attention while significantly improving computational efficiency. And yeah, let's look at the detail of the hierarchical sparse attention architecture. Hierarchical sparse attention reduces computational complexity by constructing a multi-level token hierarchy. The model builds a hierarchy structure over the input tokens, breaking the attention computation into two optimized phases: a bottom-up tree construction and a top-down context propagation. And in the bottom-up phase, parent nodes aggregate information from themselves and their children and their two children to progressively summarize information from leaf tokens into higher level nodes. Instead of attending to every token directly, tokens then use this top-down phrase to attend a set of ancestor nodes retrieved from these hierarchical trees. These nodes include parents, siblings, and higher-level summary nodes. This provides compressed representation of distant tokens, enabling highly efficient and long-range context modeling. And we also introduced sliding window attention. While the hierarchical tree handles long-range context, sliding window attention is used to capture the fine-grained local context. In this mechanism, each leaf token acts as a query that attends only to its immediate labels within a fixed window size. This captures short-range dependencies efficiently without the need to calculate pairwise interaction across the entire sequence. Uh, Instead of applying separate attention distributions, the models seamlessly integrate both methods. It concatenates the logics from the sliding window tokens and the global hierarchical attention nodes before applying to the softmax in the Triton kernels. This creates a single unified probability distribution. By using these mechanisms, the model can simultaneously consider fine-grained local context and compressed global information while maintaining efficient computation speed. And let's look at the next slide. To achieve high computational efficiency, Both hierarchical attention and sliding window attention mechanism were implemented using custom GPU kernels written in Triton. Standard dense attention requires storing the full attention matrix, which can quickly exceed the on-chip memory capacity of modern GPUs. But our implementation avoids this by fusing multiple operations you can see here, including query key multiplications, masking and software normalization, and also the value aggregations. We just integrate them into a single GPU kernel, and this significantly reduces memory traffic and improves the performance. And let's look at the most challenging part of the Triton kernel implementation. The hierarchical structure introduces additional challenges, particularly in backward pass computing gradients through the tray requires careful application of the chain rule of calculus within the Triton kernels. A single kernel would suffer from severe thread divergence because of the branching hierarchy. To solve this, we decompose the backward passing to multiple specialized kernels, each handling specific gradient computation. So let's look at the code of the Python kernel implementation. You can see here we only have one forward kernel, but we have five corresponding backward kernel. Each one has a different gradients calculation process. Okay, let's get back to the slides. And also, atomic operations were used to safely aggregate gradients across the GPU threads, ensuring correct updates even when higher level parent loads receive many more contributions than the lower level nodes. Okay, let's take a look at the results of the experiment. Uh, this is the experimental evaluation of model quality. After validating our kernels against the reference PyTorch implementations, we integrate the attention module into a 12-layer transformer, decoder-only transformer model, and evaluate it on the WikText 103 dataset. The compiler hierarchical and slide window attention model achieves the test perplexity of around 24. A comparable full attention model achieved around 22, meaning our architecture retains about 90% of the performance of the standard attention, while using a much more efficient attention mechanism. And next we do, let me have a see. We also do some ablation tests, but it's not presented here. The combined hierarchical spot attention plus sliding window attention on weak text 103. The training perplexity is dropping from 61 to 56, and the validation perplexity dropping from 74 to 70, and the test perplexity dropping from 27 to 24. So this ablation study showed that combining HSA and SWA, which is represented hierarchical attention and sliding window attention, improves perplexity by 5 to 9% compared to using each alone, demonstrated their complementary benefits. And let's look at the scalability unlock. Efficiency we can show here achieved by the hierarchical attention. In terms of efficiency, the results were great. Our optimized Triton implementation achieves average of 3.24 training speed up compared to the PyTorch implementation. More importantly, by reducing memory complexity from big O n squared to approximately big O n log n, the model can process much longer sequences. On a single 80 gigabytes NVIDIA A100 GPU card. A standard full attention transformer typically supports around 4,000 tokens length under the same hardware conditions. Our hierarchical attention model successfully process sequences up to 32,000 tokens. So there are 8 times difference between those two different architectures. In particularly, the implementation can outperform the commonly used memory efficient attention standard. It's also standard full attention in PyTorch. Once the sequence length exceeds 2,000 tokens. For the non optimized full standard attention implementation using PyTorch, the speed is 4 times faster on proposed hierarchical attention implementation. And finally, this slide shows current challenges and what we can do in the future work. There are still several challenges. First, the bottom-up tree construction process is inherently sequential, which limits how much parallelism we can exploit on the GPU. In addition, repeated projection, which happened on each layer construction, introduce additional computational overhead. And the future work will focus on optimizing these bottlenecks, exploring even longer sequence modeling, and evaluating the model on additional downstream tasks such as needle in a haystack dataset, some sentimental analysis, and some summarization tasks like a multi-new summarization. Okay, that's the last one. And let me see. Finally, it is worth noting that due to the hardware limitations, we cannot directly compare our model with flash attention optimized transformers and extremely long sequence lengths beyond like 16,000 or even 64,000 tokens. We expected that our hierarchical attention mechanism would outperform flash attention-based full attention models and very long sequence length. However, this hypothesis still requires further experimental validation, but such experiments would require substantially larger GPU memory or distributed training setups. Uh, so at a shorter sequence length, flash attention to optimized transformers can still achieve faster training speed than the proposed hierarchical attention. Okay, that's all my presentation. Thank you very much for your time.